Hello, I want to explain how the idea of confidence can be used to assess the credibility of hypotheses we want to test, and also how you can work out confidence levels by a simulation method called bootstrapping using an Excel spreadsheet. This is all far more straightforward than is conventional in statistics. I need an example to explain, so let's imagine there's a rumour that men are the miserable sex and women tend to be happier. We decide to test this by doing a survey. As you can see, the first woman in the sample has a happiness score of 9, so she's very happy, whereas the fourth one is a man with a score of 1. He's obviously very sad. If we want to find out the overall pattern, we obviously need to take averages, and the average for the women is 6, whereas the average for the men is 4.7, difference of 1.3 in favour of the women, so it does seem from the sample that women are a bit happier than men. But this is only a sample of 20 people. It's possible that if you did the same survey with all the women and men in the population, you might come to a different conclusion. So the question arises of how reliable the conclusions are that we can draw from a sample of 20 like this. This is a common statistical question, and the conventional answer is that p is 0.345. This is known in the trade as a p-value, but most people who use p-values don't know what they mean, and if you do know what it means, and you'll quickly realise it doesn't quite tell you what you really want to know, which is how likely it is that women really are overall happier than men. I'm not going to say any more about p-values here, but what I would like to do is to tell the story in terms of the idea of confidence, which makes an awful lot more sense. This graph is the confidence distribution based on this data. The horizontal axis represents the difference between the women's and the men's average happiness scores in the whole population from which the sample is drawn. So 0 means that men and women are equally happy on average, +2 means that the women are 2 units happier, -3 that the men are 3 units happier, and so on. The message of the graph should be pretty obvious. The most likely difference is 1.3, corresponding to the women being 1.3 units happier on average, obviously because this is what we found in the sample. But the true difference could be anything between about -4 and +6. Conventionally, people tend to quote the middle 95% of this confidence distribution, which is called the 95% confidence interval. This goes from about -1.5 to +4.1. The graph itself gives you a good idea of what sort of error we should expect from a sample of this size. The message, of course, is that samples of this size are not very accurate. This graph is generated from some complicated mathematics, the same mathematics that's used to produce the p-value. I won't say anything more about this maths because bootstrapping is a far more straightforward way of working it out, and also gives you a good feel for the errors involved in basing conclusions on small samples. Now to the main question. How confident can we be about the hypothesis that overall women are happier than men? Perhaps they are, perhaps they aren't. The graph gives us a good idea of how important the perhaps is. The maths tells us that 83% of the confidence is to the right of the 0 line, meaning that there's an 83% probability that women are actually happier than men. Some statisticians would quibble with the way I've gone from confidence to probability, but I think this is being over-pedantic. But use the word confidence if you like. We can also work out that, for example, there's about a 59% chance that women are more than 1 unit happier than men, but there's only a 5% chance that the men are more than 1 unit happier than the women. Now to bootstrapping and how we can work all this out the simple way. The basic idea is very simple. Imagine that the pattern in the sample is like the whole population, and use this to generate lots of samples from the whole population to see how much they vary. It's like pulling yourself up by your bootstraps without the aid of any fancy statistical theory. All you need is the idea of an average. The best way to explain is to play cards. Okay, so let's play cards. What I've done is I've written each member of the sample on one of these cards. So the one on the top, for instance, is 8F, which is the second one on the list. In other words, that's a female with a score of 8. Now, if the pattern in the population is the same as the sample, we've got lots of 8Fs, lots of 2Fs. Let's say we've got 1 million of each. So we've got 1 million of each of these 20 cards, which makes 20 million. But obviously, if we then choose a member of the population at random, there's a 1 in 20 chance that it'll be any of these cards. So to get the first member of the simulated sample, all we do is we give them a good shuffle the cards, and then deal 1, and the first card to be chosen is 4M, in other words, a man with a score of 4. Then obviously I can't deal the next one because now there are only 19 cards, so the probabilities will go all wrong. What I've got to do is I've got to replace this in the pack, shuffle again, and deal the next card, which is 7F, in other words, a woman with a score of 7, and so on. So all I've got to do is to do this to do this 20 times to get my first simulated sample, which is called a resample for fairly obvious reasons, and it's a resample with replacement because we're replacing each card, so that each time you deal a card, it's got a 1 in 20 chance of being any of the 20 in the sample. When I did that with 20 cards, the average of the females was 7 and the average of the men's was just over 4.6, which gives a difference of plus 2.4 in favour of the women. The next time I did it, there was a slight difference in favour of the men, all of which gives you a feel for the way samples from this sort of population can vary. But obviously to find out the sort of general pattern, we need to do this a lot of times, which means we need a computer. I've set this spreadsheet up to do various things, including bootstrapping. If you're interested in any of the other things it'll do, if you click on some of the sheets tabs at the bottom, that should explain. So what we've got here is the data you saw before, there it is, and the spreadsheet has worked out the mean of the females is 6, the mean of the males is 4.7, so the difference between the two means is 1.3. Now the next stage, of course, is resampling with replacement, and that happens here. Sorry, click again. Yes, if I click on the single resample, you see we've got, it says there, with replacement in both columns. And if you click on that, there are various other possibilities that I won't go into. And what's going on here is the exact equivalent of the game playing cards that you've just seen. In other words, I've chosen one of the cards, then put it back, and so on 20 times, and the sample we've got is here. So the first thing in the sample is 1M, in other words, a sad man. The next one is a fairly happy female, and so on. And the thing has done the sums, and it turns out that the mean of the females is 6.9 and the mean of the males is 3.1. Now these have of course been chosen at random, and to show you that at work, if you press the function key F9, which recalculates the spreadsheet, everything changes. So with that shuffle, the first one is 7F and so on, and now the females have an average of 5.9, the males are 4.8, so this is a little bit closer, 1.04 in favour of the females. Let's just try another one. That's 1.4 in favour of the females, 1.8 in favour of the females. This one is now in favour of the males. The male average is now 6.7, the female average is 5.8, so the difference is now minus 0.84. And I think this should give you a good idea of the way in which sampling at random from a population like the one we've got, as simulated by saying we've got lots and lots of people like the first individual, lots and lots of people like the second individual, and so on. The sort of pattern you get goes like this. Okay, so the obvious next stage is to do this lots of times. So on this screen, what we've got is 20 resamples, and the first one is 0.42. If we go back to this tab, that's this one here, plus 0.42. There we are. The next one is 2. The next one is 0.33. And in fact, these turn out to be all positive. There's no instances where the males have turned out to be happier than the females, and that itself should give you a sort of a feel for how unlikely that is. What I've done now is I've drawn a histogram here, and so for instance there are 2 centered on 2, in other words between about 1.9 and 2.1. Those 2 are the 2 we've got there, and there are 4 in the bar centered on 1.4. Obviously, if I press F9 again to recalculate, everything changes as you would expect, like that. Now, obviously, to get the sort of overall answer, to get an answer that will give you the best idea of the probabilities, we need more resamples. And I've set this thing up so that there are 2 options, but by the way, all the orange cells hide a menu. So if I set that to 1,000 resamples, what's going on now is this goes down for 1,000 rows. There we are. So it goes on and on. And now if I press F9 again, it recalculates, but it takes a little bit longer. And the reason, of course, is it's got more work to do. Okay, let's just recap on what we've got. If we imagine a population comprising, say, 1,000 people like the first woman here, a 9F, 1,000 like her, 1,000 like her, 1,000 like him, our sad man, so we've got 20,000 people, and if we take random samples of 20 from this population, which is what the resampling or the card trick does, the pattern we're going to end up with is this. In other words, the means of the samples, and the difference of the female and the male mean in the sample will range from about minus 2.5 to about plus 4.5, which of course is a big range. Now, what we're actually interested in, of course, is what we can infer from a single sample. And the average of the single sample we've got is 1.3, about there. So if the sample we get is down there, that will obviously be in error. It will underestimate the truth by, I don't know, about 4 units. If, on the other hand, we get one of these up here, and remember, it's a complete matter of randomness whether we get one there or one there, this will overestimate the truth by about 4 units. So what we can say is that the error in our assessment of the mean is about plus or minus 4 units. In other words, something between there and there. But this, of course, is just what this graph shows us. So in other words, we can interpret this graph not just as showing us how much the resamples vary, but showing us how how much confidence we can have in concluding, say, that the truth is minus 2.5 based on our one sample. In other words, this gives us a confidence distribution. If you think about what I've just said in a bit of detail, you'll probably find there's a few flaws. Most obviously, I've sort of mixed up plus and minus, and also, of course, the real population won't be like 1,000 copies of our sample. It'll be a bit different, and that means that the answers we're going to get aren't going to be dead right, but they're ballpark figures. They're pretty good. So this then is what the confidence, we can think of this as a confidence distribution. Okay, so that's the way this works. So in practice, if we forget a few quibbles, you can think of this as a confidence distribution. Incidentally, the fact that the rationale behind this is based on common sense, and it's possible to see what's going on without any complicated mathematics, means that the bugs, the problems in the reasoning, are actually a lot easier to see. Now, how does this compare with the mathematics? Well, the formula-based confidence distribution looks like that, which, as you can see, goes from about -3 to +5. If we go back to the other one, that is very similar. In other words, this does give you answers very close to the mathematical answers. Let's just look at some of the detailed answers. If we want the percentage of confidence above 0, in other words, our confidence level in the hypothesis that the women are happier, in other words, that bit up there, I can do that by putting 0 in here, which is labeled percentage above, and this comes to 83.7%. And I think, remember earlier, based on the confidence mathematical confidence distribution, that was 83. If we put percentage above 1, which will be the this is the confidence above that point there. In other words, the confidence or the probability that the females will score at least 1 more than the males. That's more or less identical before. I think before it came to 59%, now it's 58.5, and if we put -1, that's going to come to again, -1 means that 95% of the probability is up there, which obviously means 5% is down there, which is the same result as we got before, namely about the probability of the men being more than 1 unit happier than women is about 0.5%. Okay, so there's various other things you can do this. I'll just show you one more thing you can do with the bootstrapping, well, with this program, and that is that you might wonder what happens if we take a bigger sample. So the problem with a sample of 20 is obviously that it's rather small, it's not very accurate. So what happens if we make it a bit bigger? Easily done. If we copy the original sample and go down a bit to the row below there and just paste it in, there we are, all in. And now, as you see, we've got a sample size of 40, but as the numbers are the same, it's the same difference of 1.3. Female mean is 6 again. If we go to the lots of resamples, this of course has been rescaled. Instead of this, now goes from about -2 to about +4, which, if you remember back from before, is a bit more crunched up. This went from -3 to +5. So this reflects the fact that samples of 40 are likely to be more accurate. So the percentage above -1 is now
98%, 98.8%, 99%. In other words, we can be more sure. The if we put naught in there, the percentage, the probability of the females being happier. I think before that was about 83%. Now with the same sort of data but more of it, we can have more confidence. In other words, the confidence level or the probability level has now gone up to 90%.
Okay, that's it. I hope I've convinced you that confidence levels are a helpful way of assessing the credibility of a hypothesis, and also that bootstrapping is a really good way of actually doing the sums so that you can see how it works. The spreadsheet I've showed you is pretty flexible. You can use it for doing different kinds of simulation models, and also obviously you can put your own data